Hello everyone, welcome to another episode of Aerospace Engineering with Brian McNulty. Today's episode is going to be about the properties of matter, and this will be an adaptation from an introductory chemistry book. So the things that we will discuss today are going to be atoms and molecules. We'll talk about the scientific method. We'll talk about classifying matter, and we'll talk about what a physical change is versus a chemical change. And we will also look at units of measurement and the different systems that we use to do those. So atoms are submicroscopic bits of matter that determine the behavior of our physical world. These atoms can have charges that attract and repel one another, and those atoms that have certain net positive or net negative electric charges can come together to form molecules. Molecules are just bigger particles than atoms that are formed from combination of atoms, and those molecules are typically responsible for the properties of matter we observe in the universe. Now, atoms and molecules, so atoms go on to form these molecules, and like I said, they're formed by these tiny electric forces. These tiny electrical connections between these atoms are called chemical bonds. Now, there are several different types of chemical bonds to learn about, but we'll save that for more advanced material. This here is a model of a carbon monoxide molecule. So we can tell that the properties of atoms and molecules, and the properties of molecules more specifically, can change drastically with just one change in the atoms that make it up. A good example of this is carbon monoxide. It turns out that when we are breathing oxygen, the carbon monoxide in the air, like the molecule that we just saw, is just the right shape to fit into hemoglobin, which is the oxygen-carrying molecule in our blood that is responsible for delivering the oxygen to our brain. It turns out that this carbon monoxide molecule is actually able to replace the oxygen molecule on the hemoglobin, thus causing some biological issues. Carbon dioxide, on the other hand, doesn't bind with the hemoglobin or the oxygen-carrying molecules in our blood as well, because it has an extra oxygen molecule that makes it not the right fit for the hemoglobin molecule. And so we're able to breathe much more of that, fortunately, because a lot of our vehicles that we use to travel emit much larger quantities of carbon dioxide, or CO2, rather than carbon monoxide, or CO. The carbon monoxide molecule is interesting because it's present in the atmosphere that we breathe in. The reason why it can be dangerous is because the blood-carrying molecule, hemoglobin, in our blood that is responsible for transporting oxygen to our brains can actually accept this carbon monoxide molecule just as it accepts oxygen, therefore taking up space on the hemoglobin molecule, and instead of transporting oxygen to our brains, transports instead carbon monoxide, which is not what our brain needs. So the scientific method is a way for scientists and engineers to form the theories and ultimately learn more about the universe. So it goes a little something like this. So you have to define a problem. There has to be a problem to solve or something. That's what you're trying to get at. You're trying to figure out why something is happening or how something is happening. You know, you make observations about that problem's environment, and you kind of see, conduct a lot of initial research and see what is going on with this problem and what is causing it, what could be causing it. Make a list, form a hypothesis. This is an initial guess, essentially. It's an educated guess on how to solve this problem, and it can come in many different forms. And then from this hypothesis, you can design an experiment, and the experiment will deal with any outliers or any extraneous variables that may not be relevant to what you're looking for. If your experiment does not agree with your hypothesis, you need to go back and you need to either redefine the problem, you need to make more observations, or you might need to modify your hypothesis. If the experiment does agree with the hypothesis, then you can go on to publish a theory. And that theory can be tested by others and falsified as needed. It's important to emphasize that when you're looking at the scientific method, that when your experiment does not falsify or it concludes that your hypothesis is only partially true, then you have to redesign the experiment and try again, or maybe your hypothesis is just wrong and you need to make more observations to learn more about that thing. So matter can be classified by the state that it's in, and I've listed 4 of them here, although the first 3 are going to be the only ones we look at until more advanced topics. So matter can be classified as a solid, it can be classified as a liquid, or it can be classified as a gas. Let's take a look at the difference between those 3 right now. With solids, the atoms within the solid are packed very close together. Now, these solids can take on both amorphous or crystalline forms. They are said to be incompressible, and because they are so close together, the atoms have very little kinetic energy, and therefore they don't move around very much. 2 types of solids we'll be looking at are the crystalline solid and the amorphous solid. Now, to start with the crystalline. This crystalline solid, if a solid is crystalline, it will indicate that there is a repeating atomic structure that makes up this solid. In repeating atomic structures, you can picture a very ordered lattice with a repeating pattern of atoms that are holding it together. On the other hand, we have amorphous structures, which are more random atomic structures, like this piece of cotton candy that you see. On the atomic level, you would observe that there's no repeating pattern in the atomic lattice that holds this solid together. Typically, crystalline structures will be stronger than amorphous structures. So like a solid, a liquid is compressible. The atoms in a liquid are close together, but they're not packed in. And so this allows the atoms to have more kinetic energy than they would if they were in a solid. Now moving on to gases. Gases are compressible, and that just has to do again with the fact that the atoms are even more dispersed than they were in a liquid. And so that leaves some space in between them, and that leaves room for compression. Atoms can also have more kinetic energy in a gaseous state. So that was the classification of matter by its state, which can be a liquid, a solid, or a gas. And we just learned about a few of those properties. But now we're going to look at a different classification. So we can also classify matter by its composition, and we can do this by deciding if the matter that we're looking at is a pure substance or if it's a mixture. Now, if we're looking at a pure substance, those pure substances are defined by just being made of only one component. Now, the components can be atoms or they can be compounds or molecules. So an example of some pure substances would be like liquid nitrogen, helium gas, and water. Now you might be thinking, okay, wait, hold on a second. Water is actually 2 atoms, right? It's a hydrogen atom and it's an oxygen atom. So why would that be considered a pure substance? Well, remember I said that the components that it is made out of can be molecules. It turns out water is a molecule, and since there's only water molecules in, let's say, a glass of water you're drinking, then it is indeed a pure substance. Now, if we go on to mixtures, those are made up of 2 or more components. Now, the components again can be atoms or molecules, but we have an example here where we say sweetened tea. Okay, well that's just water with extra ingredients. It has sugar in it, so we're going to want to take that into account. That makes it 2 or more components. The air that we breathe is a mixture of nitrogen and oxygen, and it's also got pollutants and carbon monoxide in it, so that makes the air that we breathe a mixture as well. So, classifying by composition, we can say that matter can be a pure substance or a mixture. There are two ways in which we can classify mixtures, not pure substances. Two ways in which we can classify mixtures, and those are known as homogeneous and heterogeneous. Homogeneous mixtures contain a substance that is uniformly distributed throughout a volume. For example, this cup of coffee is a homogeneous mixture because the distribution of the chemical compounds inside of this glass are uniformly distributed. Same goes for this glass of water. You can see that the molecules of water are uniformly distributed. There's not like some other substance clumped up somewhere in it. But, and I hope this works out okay, if I take this chocolate stuff and I put it in here, now something cool kind of happens. You see you have like this layer. This is definitely heterogeneous. You can see where the substance is separated from the water, and we actually have some pretty cool stuff going on in there. I'll put a little bit more in here so you can kind of see it at the bottom, and it kind of just stinks to the bottom. It doesn't uniformly stick together, and so that's pretty cool. That is known as a heterogeneous mixture. So sometimes chemists want to like isolate certain compounds or salts from water, and so you need to have some methods of separation. And to achieve separation, I'm just going to go over 3 different types of methods that are used. The first one I'm going to talk about is called decanting, and that's essentially where you have like maybe a bucket of moist sand or soil or something, and you want to get the water out of it. So one way to do that would just be slowly pour the water out of the bucket of sand without bringing the sand along with it. You can imagine this might take a little bit of time to do. A more time efficient method would be to, let's say you have some salt water and you want to boil it to get the salt out. Well, that process is called distillation. Essentially what happens there is you exploit the boiling point of water so that it kind of rises out of the salt solution and it just leaves the salt remaining in the bottom of the collection beaker. And then the last one is called filtration. This one is probably the one that we're most familiar with in our everyday lives, and that's just passing, let's say, a non-pure substance or a mixture through a filter, and the filter has membrane holes that are, let's say, big enough to let the water through, but not big enough to let a salt through. And so the only thing that's going to pass through the other side of that membrane or the other side of that filter is going to be the smaller molecules that can make it through that filtration membrane, thus filtering the water. And that will give you your 3 methods of separating. Okay, now we can kind of talk about something a little different. It's going to be the difference between a physical change and a chemical change, and why it's important to know the difference. Essentially, a physical change is when the substance that you're dealing with changes appearance due to maybe a temperature change. So let's say that you are heating up a boiling pot of water and you can see that it's changing into a gas. That's a physical change, because even though the water becomes a gas, all it really does is transition states. It goes from a liquid to a gas, and it's still water. It's water vapor though, but it still has the same chemical properties. A chemical change, on the other hand, would occur if you, let's say, poured some acid into a bucket of water. The water molecules will bind to the acidic salt that you have added, and it will actually change the chemical composition of the substance in the bucket. So instead of just having water, now you have some type of acid because of the addition of that acidic salt. So those are the differences between physical and chemical changes, as we will be discussing them further on. Okay, so next we're going to talk about units of measurements. There are 2 different systems that we use as scientists and engineers to measure things. And these systems are known as, one, the metric system, and two, the international system of units. We'll mainly be dealing with the metric system because it's what's known as base 10, and that makes calculations very easy. And so I'm just going to talk about that mostly, and then we'll go into conversion factors using dimensional analysis. So the metric system, it uses meters to measure length or distance. It measures kilograms to measure mass. The second is used to measure time. The Kelvin unit is used to measure the temperature. A mole is simply the amount of a substance in a given volume. An ampere is the amount of electric current in a wire. And a candela is... This is just a way of converting between units of measurement given different conversion factors. So if you know that there's 1,609 meters in 1 mile, you can convert from miles to meters or meters to miles using conversion ratios. And we'll take a look at how to do that right now. Alright, so for this unit analysis, let's say that for a particular problem they want the answer in centimeters, but you just got 6.3 inches for your answer, but you need that in centimeters. Well, we know from most basic physics textbooks or unit conversion tables that 1 inch equals 2.54 centimeters. This is pretty cool. So we know that information, that the conversion factor is that there's 2.54 centimeters per every inch. Well, if you are multiplying these, you know that the inches will cancel out, and once you rewrite that, you get 6.3 times 2.54 centimeters. The centimeters didn't cancel with anything. But now, what you have is a perfectly nice thing that we all know how to do, and we just go 6.3 times 2.54, and therefore you can say that there are in fact 16.002 centimeters in 6.3 inches. So that's how you do that conversion factor, but let's take a look at one that's a little more complicated. Okay, so now we're going to we'll do some volume conversions here. So we know that 1 cubic inch equals 0.0164 liters. Once we have this information, we can freely convert between these two volume units as much as we please. So let's say that I want to know, how many cubic inches are in, let's say, 5.7 liters. Okay, so we write down what we're initially given, which is 5.7 liters, and we're given this conversion factor here, 0.0164. So what we're going to do is we're going to multiply by some ratio that's going to convert this 5.7 liters into cubic inches. How we do that is we want these liter units to cancel so that our final answer is in cubic inches. We know that if we have like a fraction and the same thing is on the top and the bottom, that fraction just equal to 1. And so if we have this 0.0164 liters, that's equal to 1 cubic inch. This whole thing, including the units, just goes to 1 and it changes the units. So we cancel out these liters here, and then our answer in cubic inches ends up being this 5.7 divided by 0.0164. Remember, the units canceled, so I'm not going to include them anymore. And then we just multiply that by the 1 cubic inch. Well, it turns out that the answer to this problem ends up being 5.7 divided by 0.0164, and that gives us an answer of 347.56 cubic inches. And so that is how you convert between different volume units. Let's take a look at a slightly more complicated example. Okay, so let's say that we are tasked with converting square centimeters to square inches. In other words, how many square inches are in a given square centimeters? Well, we know that, let's say that we've got 7 square inches. That's the area that we're given in square inches, but we need it in square centimeters. So what we're going to have to do is, we don't have a conversion rate for that, but we do have a conversion rate for regular centimeters to regular inches. So we know that 1 inch, remember I put this unit on the bottom to match these two, so they cancel. 1 inch is equivalent to 2.54 centimeters. Cool. That's all fine and dandy, but these units still don't cancel out. You realize if we divide these two values, we'll end up getting inches to the first power up here, and this one will cancel, so we'll just have inches to the first power. What we do to correct for that is we put a parentheses around the conversion factor, and we square it. That gives us, and I'll rewrite the entire expression, that gives us this right here. Notice how I'm going to square every single, this 2 gets distributed. If you remember your algebra, that's how that works. 1 squared inches squared. Now we can cancel these, since we've distributed this 2 to each number in this fraction. And this leaves us with 7 over 1 squared times 2.54 squared centimeters squared. Okay? Plugging these values into our calculator, we end up getting 7 times 2.54 squared. And that is going to give us a final answer of 45.16 square centimeters is equivalent to 7 square inches. And that's the whole meaning of that problem. So just take a quick look at what we did. Okay, so I hope you guys enjoyed the video. There will be much more in chemistry, physics, math, and engineering to come, so stay tuned. Make sure to subscribe and like my video, and let me know how you feel about it in the comments. Alright, I'll see you guys on the next episode. Thanks for viewing.